Welcome to our journey into the origin of tetrapods. Imagine swimming in a supportive pool all your life, feeling weightless, and then suddenly having to pull yourself onto a hard, dry deck. Gravity pulls you down, the air feels different, and swimming motions no longer work. This is the exact scenario our ancient fish ancestors faced millions of years ago. Today, we will explore how these aquatic creatures adapted to survive, breathe, and walk in a harsh, dry world, marking one of the most important makeovers in the history of life on Earth. Now that we have set the stage, let us look at when and why this transition happened. The origin of tetrapods refers to the monumental evolutionary shift from lobe-finned fishes, known as Sarcopterygi, into the very first four-limbed vertebrates called Tetrapoda. This leap occurred during the Devonian period, roughly between 390 and 360 million years ago. Why did they leave the water? Their shallow, swampy habitats were drying up, forcing them to adapt to terrestrial environments to survive. This ancient history is deeply personal to us because without this milestone, human beings would not exist. Every land-dwelling vertebrate today traces its ancestry back to these brave pioneers. Understanding why they moved to land brings us to how their bodies changed to make it possible. To survive in this new, harsh environment, these ancient fishes had to undergo massive anatomical re-engineering. Most notably, their delicate fins transformed into sturdy limbs ending in digits, which are the fingers and toes we have today. But limbs were not enough. They also evolved lungs to extract oxygen directly from the atmosphere, and they developed much stronger vertebral columns to support their body weight against the relentless pull of gravity. Even their sensory organs had to be modified so they could hear and see clearly in the air rather than underwater. These anatomical changes were not random. They were demanded by the laws of physics, which leads us to the mechanical challenges of leaving the water. In an aquatic environment, an animal experiences a powerful upward push called buoyancy. This buoyant force cancels out most of the downward pull of gravity, meaning a fish does not need thick, heavy bones to support its body weight. However, the moment that animal steps onto land, the buoyant force provided by the surrounding air drops to practically zero. Suddenly, the animal must support its entire mass using only its skeletal system and muscles. This dramatic shift in physical forces is the primary driver behind the evolution of robust tetrapod skeletons. To truly grasp this dramatic change in physical forces, let us look at the mathematical equation that governs it. The formula for effective weight calculates the actual force an animal feels pulling it against the ground. It equals the true gravitational weight, which is mass times gravity, minus the buoyant force, which is the fluid density times the body volume times gravity. The symbol WEF represents this effective weight in newtons. The symbol m is the animal's mass, and g is the acceleration due to gravity. The Greek letter rho represents the density of the surrounding fluid, and v is the volume of the animal. When the fluid density rho decreases, like moving from water to air, the buoyant force drops, causing the effective weight to increase massively. Before we move on, let us see this formula in action with a concrete example of a primitive fish like Tiktaalik submerged in water. We are given a mass of 40 kilograms and a body volume of 0.039 cubic meters. The density of water is 1,000 kilograms per cubic meter, and gravity is 9.8 meters per second squared. We plug these values into our effective weight equation. The true weight is 392 newtons, but the water provides a massive buoyant force of 382.2 newtons. Subtracting these gives a final effective weight of just 9.8 newtons. Physically, this means the fish feels almost weightless, allowing its delicate fins to easily support its body. Now that we have calculated the weight underwater, let us see what happens when this exact same animal drags itself onto the muddy shore. The true weight remains 392 newtons because the mass has not changed. However, we must now use the density of air, which is only 1.2 kilograms per cubic meter. Multiplying this by the volume and gravity gives a buoyant force of a mere 0.46 newtons. Subtracting this tiny upward push from the true weight leaves a final effective weight of 391.54 newtons. Physically, this means the animal is suddenly supporting nearly 40 times more weight than it did in the water, perfectly illustrating why thick, sturdy bones were absolutely necessary. This massive increase in effective weight brings us to another crucial physical challenge. How did they actually lift themselves? As early tetrapods developed limbs, their bones acted as biological levers to help hoist their heavy bodies off the ground. In any lever system, there is an input distance, which is where the muscle attaches to the bone near the joint. There is also an output distance, which is where the foot actually pushes against the ground. The relationship between these two distances dictates the mechanical advantage of the limb. Understanding this leverage is key to seeing why early land animals had such unique, sprawling postures, and why their muscles had to work so incredibly hard. To quantify this leverage, let us look at the mathematical formula for mechanical advantage. Conceptually, this ratio dictates the fundamental trade-off between the force a muscle must exert and the speed at which the limb can move. The formula states that mechanical advantage, or MA, equals the input distance divided by the output distance. The symbol dIn represents the distance from the pivot point, or joint, to where the muscle attaches. The symbol dout represents the distance from the joint to where the limb touches the ground. If the input distance is much smaller than the output distance, the mechanical advantage decreases. Physically, a lower mechanical advantage means the muscle must pull much harder to generate the necessary force at the foot. Now that we have our formula, let us apply it to a primitive tetrapod's front limb to see what this ratio looks like in reality. We are given an input distance of 0.02 meters, which is where the triceps muscle attaches to the elbow joint. We are also given an output distance of 0.10 meters, which is where the foot pushes against the ground. By dividing the input distance by the output distance, we calculate a final mechanical advantage of 0.2. Physically, because this number is less than 1, it tells us that the limb is built for speed and range of motion rather than strength, putting the muscles at a severe mechanical disadvantage. This severe mechanical disadvantage leads us directly to the formula for required muscle force. Conceptually, this equation tells us exactly how hard the animal's muscles must pull to overcome the poor leverage of its limbs. The formula states that the muscle force equals the output force divided by the mechanical advantage. The symbol F muscle represents the internal force generated by the animal's muscles, measured in newtons. The symbol F out represents the output force, which is the portion of the body weight the limb needs to lift, also in newtons. MA is the mechanical advantage we just learned about. Physically, as the mechanical advantage decreases, the required muscle force increases dramatically, meaning the animal must expend massive amounts of energy just to stand up. Let us put this muscle force formula to the test using the mechanical advantage we calculated earlier. We want to determine how much force the triceps muscle must generate to lift a body weight of 100 newtons. We are given our output force of 100 newtons, and we know our mechanical advantage is 0.2. By dividing 100 by 0.2, we arrive at a final required muscle force of 500 newtons. Physically, this is a staggering result. It means the early tetrapods muscles had to pull with a force 5 times greater than the actual weight it was trying to lift. This incredible demand explains why these animals evolved massive shoulder and pelvic bones just to anchor their muscles. Having proven the immense physical challenges of gravity and leverage, let us visually examine the brilliant evolutionary engineering that solved them. On screen, you are looking at the gradual transition of limb bone structure across 3 distinct stages. On the far left, we see the fin of a lobe-finned fish. Notice how the humerus, radius, and ulna are already present, but they are tightly packed inside a hydrodynamic fin. Moving to the middle, the transitional fossil shows these bones elongating and early wrist structures beginning to form as the animal started bearing weight. Finally, on the right, we see the fully developed early tetrapod limb. The bones are thick and robust, and distinct digits have formed to grip the land. This diagram perfectly illustrates how living tissues re-engineered themselves to conquer a new world. As we conclude our lecture, let us reinforce the most important ideas from this incredible evolutionary journey. First, remember that tetrapods evolved from lobe-finned fishes during the Devonian period, driven by drying habitats. Second, the transition from water to land was fundamentally a physics problem. Losing the upward push of buoyancy meant their effective weight increased massively, demanding stronger skeletons. Third, their new limbs acted as levers with very low mechanical advantage, which required them to evolve massive muscles just to lift their bodies against gravity. You have now covered the full scope of how our aquatic ancestors conquered the land. This monumental shift was not just ancient history. It laid the biological and mechanical foundation for all terrestrial vertebrate life, including ourselves.